Today we're talking about independent and dependent events. So we want to find the probability of independent events and find the probability of dependent events. So it's important to learn the difference between the two of them so that you can distinguish between them. Now the one thing is that distinguishing between them is an important thing, but the most important thing is that you understand how to find the probabilities. And finding the probabilities is really the same process, whether it's an independent or a dependent situation. But you need to know which is which. All right, and it's really pretty simple as far as determining the difference between them. So events are independent if the occurrence of one does not affect the probability of the other. Right? And usually when we're doing things with independent events, that would be like flipping a coin, rolling a number cube, those are always going to be independent events. Where things get a little bit different, or they change between independent and dependent, is when you start dealing with stuff where you're taking something out of a bag or a card from a deck of cards. And if we put that card back into the deck after we pull it out, nothing has changed because I have the same total number of cards. Right? When we have dependent events is when the total is going to change. Right? So basically, if I take a card out and I set it aside, so instead of having 52 cards, I'll have 51 cards. Now I have dependent events because what happened with the first card is affecting what happens with the next card. Right? So independent events would be a situation where the total options I have, basically, doesn't change. Dependent events, the occurrence of one does affect the probability of the other. And so that's a situation where what I've done first, if it's going to affect what I'm going to do now, because it changes the total, then I have dependent events. Right? So for instance, if I have a bunch of marbles in a bag, all right, if I pull one out and I set it down, now I have one fewer marble in the bag, and so the probability of something happening is now changed, so now we have a dependent event. Okay? So independent, probability of one does not affect the probability of the other. Dependent, the probability of one does affect the probability of the other. Okay? All right, so we want to tell whether these sets of events are independent or dependent. You select a card from a standard deck of cards and hold it. A friend selects another card from the same deck. All right? So there are 52 cards in the deck. If you take one out, and then you hold on to it, and then your friend takes one out, well, once you've taken that one out, there's now only 51 cards left. So we have, and those are dependent events then. All right? Because holding on, to your card changes the probability. For your friend. Flipping a coin. All right. Well, think of it this way. Every time I flip a coin, how many different options do I have? If I flip a coin, I've got how many options, Scott? 2, heads and tails. All right, if I flip it again, has it changed? Okay, if I get a head first, does it change that? No. Okay, so the results of the, I don't have it there. Okay, results of the first toss. The results of the first toss don't, or do not affect the result for the second toss. So these are independent. Okay? So the thing is, when you're thinking about independent or dependent, think about the sample space. All right? So the total number of possibilities there are. If the total number of possibilities isn't going to change, they're independent. If it is going to change from the first one to the second one, then they're dependent. Okay? All right? So answer these two. All right? Suppose an experiment involves flipping two fair coins. The sample space of outcomes is shown by this tree diagram. Determine the theoretical probability both coins land heads up. Okay? So we have four options, four possibilities. If the first one is a head, then you can either get a head or a tail. If the first one's a tail, then you can get a head or a tail on the second one. All right? So there's actually four different things that could happen in this situation. And so you've got to figure out which of those are, between those four, which of them is going to give you two heads. Okay, both of them landing heads up. All right, and so when we use the tree diagram, we're always looking for this column over here. All right, and so we've got a head, then a head. So there's four possibilities that can happen. All right, and one of them is going to give us heads, heads. So I could have heads, 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 tail, tail, head, and tail, tail. All right. So we think about, if we look back at separate theoretical probabilities of each coin landing heads up, the theoretical probability in each case is 1/2. The product of these two then is 1/4, because if we multiply them together, we get 1/4. So finding the probability of independent events says if A and B are the two independent events we're talking about, then the probability of A and B happening, okay, is equal to the probability of A times the probability of B. So we are going to multiply the probabilities of those things happening. And we're actually going to be doing that whether it's independent or dependent. Okay? But with independent, it doesn't change. So an experiment consists of randomly selecting a marble from a bag, replacing it, and this is a key word here, is the fact that we are replacing it. Okay? That means that I'm still going to have the same amount of marbles in my bag. Then selecting another marble. The bag contains 3 red marbles and 12 green marbles. What is the probability of selecting a red marble and then a green marble? So we have independent events here because of the fact that we are replacing the first marble we pulled out. Right? So that means that our probabilities are going to be the same. So if we said we were not going to replace it, then that would make it dependent. Right? But replacing it is independent. So the probability of getting a red, then a green marble is equal to the probability of red times the probability of green. So the probability of red is 3/15. Probability of green is 12/15. Right? And when we're doing this multiplication, we're always going to leave our answers in fractions. And so if you can simplify the fractions to start with, helps you with your multiplication. So this is 1/5. 1/5 times 4/5. So there's a 4 in 25 chance that you're going to get a red and then a green. So what does that really mean? That means if I do this 25 times, okay, I'm going to get a red one and then a green one 4 times. All right? So if I put the bag of marbles in front of me, all right, and I started pulling out, I pull one out, all right, look at it, put it down, pull another one out, look at it, okay, then if you did it 25 times, 4 out of those 25 times you would expect would be a red one and then a green one. coin is flipped. Oops. 4 times. What is the probability of flipping 4 heads in a row? Now the thing about the independent events is that it doesn't matter how many times you do it, okay, the thing, you're still going to be multiplying the probabilities together. So here I want the probability of getting a head, then a head, and a head, and then a head. Right? So 4 different things are happening. Right? So that means then we're doing the probability of a head times probability of a head, probability of a head, oops, times the probability of a head. Right? So Chase, what's the probability when I flip a coin I get a head? How many sides are there to a coin? How many heads? Okay, so 1/2. So we take 1/2 times 1/2, because it always stays the same with a coin. Doesn't matter how many times you flip it, the probability of getting a head is still always 1/2. You know, I had somebody tell me 4th hour the other day that it's actually, they say that it's more than that, so, but it's all right. So this is 1/16. So we would figure that if I did that 16 times, okay, that one time I would get heads, 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 and heads. Right? Or if you did it 160 times, and you would expect that it would happen 10 times, I would get 4 heads in a row. Right? So we got to remember that that's theoretical. It's what we would expect to happen. Doesn't mean it's going to happen all the time. Okay? All right. So I'll answer these 2. Okay, dependent events. Suppose an experiment involves drawing marbles from a bag. Determine the theoretical probability of drawing a blue marble and then drawing a second blue marble without replacing the first. Now, key to this is it says that it's without replacing the first one. Right? So if we don't replace the first one, don't put it back in, now I have 1 fewer marble in the bag, and now it changes the probability, so we're talking about dependent events now. So if there were 9 marbles in the bag to start with, and if I drew out a red marble on the first draw, that means 3 of the 9, okay? So one of the red marbles is now gone. So there's only 8 marbles left, and if I was going to draw a red marble a second time, now I'm only talking about 2 out of 8 instead of 3 out of 9, okay? So when there's no replacement, or without replacement, which is what happens with dependent events, then we have to take into account what happened with the first one to get the second one. Now, the point is that the probabilities are still going to be found by multiplying. Right? It just reads a little bit different. It says if A and B are dependent events, then the probability of A and B is equal to the probability of A times the probability of B after event A has already happened. So in this case here, the probability of doing red and then red is going to be 3/9 for the first red one, but then times 2/8 for the second red one. So because I have 1 less marble in there, the denominator now has reduced by 1. And since I pulled out a red, the numerator also has reduced by 1. So here I got 3/9 for the probability of A, but then the probability of B after A, my total of both has reduced by 1. So we have to take that into account. Snack cart has 6 bags of pretzels and 10 bags of chips. Grant selects a bag at random, and then Iris selects a bag at random. Right? There's a probability that Grant will select a bag of pretzels and Iris will select a bag of chips. Well, of course, if they're at a snack cart, Grant's not going to give his pretzels back before Iris selects her chips. So we have dependent events here because what he's done now affects the total of all of them. All right, so we want to know what is the probability of pretzels, then chips. And this is dependent because he's not going to put his pretzels back before she takes her chips. All right, so let's see, we've got 16 bags altogether. So he takes one of the bags of pretzels, so that's 6 out of 16. But since he's chosen a bag of pretzels, there's now only 15 bags on the cart, and 10 of them are chips. All right, so we get 3/8 times 2/3. Which those 3's will cancel, and we get 1/4. So there's a 1 in 4 chance that he will grab a bag of pretzels and then she'll grab a bag of chips. Okay. But the fact is that when we're doing this, when it's without replacement, dependent events, the denominator for the second fraction is always going to be 1 less than the denominator for the first fraction, all right, because of not replacing it. All right. Okay, answer these. So independent events and dependent events, remember that independent events, right, the probability doesn't change. All right, so if they're replacing it, that means we're keeping the same probability. With dependent events, we know that the probability is going to change, so we're still going to be multiplying when we calculate them, but we have to remember to reduce our denominator when we're doing those. All right?